So good morning, good afternoon, good evening. Thank you very much to join us today for a next exciting talk that will be done today by Professor Ibrahim Elfadel from Khalifa University in Abu Dhabi, United Arab Emirates. And as you can see, the talk is about machine learning methods in VLSI computer-aided design. But before starting with his presentation, I would just do some brief announcements about next talks. No? So next week we have also another exciting talk by Dr. Lou Schaffer, that he is now in Howard Hughes Medical Institute. Before he spent a long time with Cadency, and he's going to talk about the electrical design of biological systems. What can you learn from the brain of a fly? Then the week after, we are going to have a talk by Dr. Yervan Zorian. He's at Synopsys in USA, and the talk will be about safety and reliability challenges in today's autonomous vehicles. Then July starts with a talk by Fernando Silveira from University of República in Uruguay. He's going to talk about wearable medical devices, sensing and empowering from a distance. So another nice talk for sure. And then we all have defined talks for July and some for August also. So we have already defined talks with Professor Elkin Roa from Colombia, also Małgorzata Jeski from Portland University, also with David Atienza from FFL Switzerland, and several others. So we plan to have the 2021 season till November this year. No? But if you lost the talks done last year, you can go to the YouTube channel that you are now. You can see the recorded versions of all 2020 talks and also several ones from 2021. So normally each Tuesday there is a new recorded talk that is included in the channel. You have also a set of 20 industrial talks that were done last year, and also many other material like talks done in microelectronics school and some other events organized by our chapter here. Then we have the chip in the fields next end of August. So the deadline for SBCCI, that is another CASS society conference also. The deadline has already passed. So, but for the students, there is still open the call for papers for the microelectronics student forum. So there is still more 4 days to send the student papers. And if you want to send a paper for SBCCI, the next year edition, 2022, that I hope that will be face-to-face, will be in Iguaçu Falls. So a nice location to receive you all. And LASCAS, that is the International Conference of CASS Society in Region 9, and the flagship conference of CASS. So next edition is in Chile, hope face-to-face, first week of March. And the submission deadline is September 1st, so we still have some months to prepare your papers. And as you should know now, a set of best papers are published in IEEE Transactions on Sequencing System 2. And the papers that are selected to TCAS 2, they appear in the edition of the months of the conference normally. So in this case, it will appear in the edition related to February or March 2022. And then also consider the presentation. There is a set of papers that are selected and invited to prepare extended version to publish in TCAS 1. And So you have 2 fast paths to have a nice paper in a nice journal. And also, as you can see, LASCAS 2023 will be in Ecuador, and LASCAS 2024 will be in Punta del Este in Uruguay. Not so far from Porto Alegre, as you can go there by bus. So if you want to promote CAS activities, there is a lot of possibilities, and any CAS member can organize something and to propose it to the CAS chapter or the CAS student branch, and then to use one of the several calls that are provided by CAS with funds. So there is a student design competition with nice grants to the winners and the travel cost to go to ISCAS for 3 students when it's a face-to-face one that I hope that next year in Austin will be. Then there is the CAS outreach call that the next deadline is in 4 days in June 15. The seasonal schools call also deadline, the call now is June 15. There is the pre-doctoral grants that students can do visit to another labs and so on. There is the student chapter grants, student travel award that now, as we have the conference mainly remote or virtual conference, it's also can support the registration to virtual conference. So it's something that is a good opportunity for all CAS members. And also there is the paper awards, Chapter of the Year awards, and many other society awards that you can see in the web page. And also the CAS Distinguished Lecture Program. So now is virtual talks, but when it will start becoming able to return with traveling, CAS can support the visit of a distinguished lecturer to give a talk face-to-face in your chapter. So about the student design competition, the first level is at chapter level. So the definition of the winners at chapter level must be done by beginning of December. Then there is the second level that is regional level, and the winners at regional level have the support to travel to ISCAS to present, to participate in the finals. And CAS can support, as I already told, 3 members or 3 students of each of the teams to do the presentation during ISCAS. And as you know, next one is in Austin, USA, May 2022. And more information on the web page. If the information about the edition 2021-2022, I didn't verify if it's already there. No problem, because it's similar to the edition that was related to 2020-2021. So please prepare your teams and start working now to have a nice participation in the student design competition. And also, there is a nice promotion by IEEE. So IEEE student and graduate student membership have a 50% discount. So if you are already a member and you have not yet renew your membership for 2022, you can do now. I don't know for how long this offer will stay. And if you are not yet a member, it's time to use this opportunity to become to participate in this global network of professionals on circuits and system. But today we are here to attend the talk in a very exciting and up-to-date topic that will be done by Professor Ibrahim Elfadel, that is related to machine learning methods and VLSI computer-aided design. So Ibrahim has been professor of electrical engineering and computer science at the Masdar Institute, now part of Khalifa University in Abu Dhabi, United Arab Emirates. So if you send a paper to ICCS 2021, the submission deadline is open till July 17. It will be in Dubai, so very close to Abu Dhabi. Then you can also do a ride to Abu Dhabi. It's just about 1 hour, no, to go there.
1 hour. And 20 minutes, about 20 minutes.
Okay. It depends on the speed.
It depends on how fast you're driving, absolutely.
Yeah. So prior to his current academic position, he was with IBM in Yorktown Heights, near New York, for 15 years as research staff member and senior scientist involved in the research, development, and deployment of VLSI CAD tools and methodologies for IBM's high-end microprocessors. So between 2012 and 2019, he led 3 Abu Dhabi-based industrially funded research centers dedicated to 3D integration, IoT, and MEMS. So AB is the recipient of 6 Invention Achievements Awards, 1 Outstanding Technical Achievement Award, and 1 Research Division Award, all from IBM for his contributions to VLSI CAD. His other awards include the DEO Pedersen Best Paper Award from the IEEE Transactions on Computer-Aided Design in 2014, and the SRC Board of Directors Special Award for Pioneering Semiconductor Research in Abu Dhabi in 2018. And he was editor of 5 books. AB is the author of more than 160 referred publications and the inventor of more than 50 issued US patents. He has been actively involved in serving the profession in various organizations and editorial roles. Abby received his PhD from MIT in 1993, and he's also a member of the IFIP Working Group 10.5. So thank you very much, Professor Ibrahim, to accept our invitation to give this talk today. I already took a look in your slide. I'm sure that it's going to be a very, very nice talk. So thank you very much. And
thank you very much.
To you to start.
Thank you very much, Ricardo. Yeah, thank you very much for your introduction. Thank you very much for having me. It's a real pleasure to be part of your seminar. I've actually personally enjoyed your seminar over the past couple of years as a listener, and it's really a privilege now to be a speaker at this seminar. So my presentation today is going to be about machine learning methods in VLSI computer-aided design, and I'm actually giving this presentation out of Abu Dhabi, United Arab Emirates. Maybe I should tell you geographically where exactly I am. I'm really right in the Gulf region of the Middle East, a region that's actually pretty geostrategic right now because of its proximity to Iran and to 90% of the flow of oil in the world going through the Strait of Hormuz that you see here between Ras Al Khaimah and Bandar Abbas in Iran. This is an iconic building in Abu Dhabi. We call that the wafer building. In fact, it's actually 2 wafers that are bonded back to back, and it used to house the Abu Dhabi offices of Global Foundries. Global Foundries is one of the major semiconductor foundries. It's wholly owned by Mubadala, which is the investment arm of the government of Abu Dhabi. And through their investments in semiconductors, they have access to 6,000 patents, more than 6,000 patents. And through the GF acquisition of IBM Microelectronics, they also have access to more than 15,000 patents. Now, in terms of my own affiliation, I'm affiliated with Khalifa University. It's a very young university. It was founded in 2007. And in 2017, it merged with 2 other institutes of higher education in the UAE, the Masdar Institute and the Petroleum Institute. It's a small university, 3,500 students, undergrad and grad, with 450 faculty. It has colleges in engineering, science, and medicine. Big news in this week related to Khalifa University. For the very first time, it's the very first university in the UAE that gets ranked in the top 200 worldwide by the 2022 QS ranking. So it's a reason for joy and celebration in the UAE and also at Khalifa University. What's unique about this university is that 60% of the student population is female. This is unique from all kinds of viewpoints, including the geographic aspect. It's in the Middle East. It's also STEM. It's a STEM school, and it's really unique to find, 60% of the student population in a STEM school being female. In my own department, it's one of the largest in the region. We have 55 faculty. The university has 3 research institutes and 18 research centers. I belong to one of these research centers. It's the Center of Cyber Physical Systems. And in that QS ranking of 2022, Khalifa University was declared as the fastest rising university in Asia. So with this introduction about the geography and the affiliation, I'd like to share with you my outline. I would assume that not all the audience is CAD or even maybe possibly semiconductors. So I'm going to give you a refresher on VLSI CAD flows. And then I'll give you the context for why machine learning has become so important in VLSI CAD. And then I'll give you some concrete examples about using machine learning in VLSI CAD. And they are going to be related to various areas of CAD. They will allow me to actually give you some specific interlocks between the CAD problems and the machine learning solutions, and that's why they got selected. The alternative would have been to give you a broad view where it would be actually much harder for me to give you very specific relationships or very specific correspondence between the CAD problem we are trying to solve and the ML solution that we found. And then I will use these examples to give you some insight into some of the taxonomy of machine learning in VLSI CAD. So I'll give you some interludes on supervised versus unsupervised, on discriminative versus generative learning. And if time permits, I will add an interesting example on IC aging prediction, a very hot topic right now in terms of IC reliability, and then I will conclude my presentation. Let me give you also some context. Some of these slides are going to be of a tutorial nature, and that's because, the original set of slides for this presentation was actually part of a half-day tutorial that I gave about 2 weeks ago now at ISCASS. At ISCASS 2021. And so I hope that the tutorial nature of some of these slides will make the presentation more accessible to the audience of this seminar. So VLSI design flow, we start like in any engineering design problem with a system specification of what we would like to design, and the end product is going to be a semiconductor chip of the type that you see all over in all kinds of gadgets, computing, communication, storage, and so on and so forth. And so this CAD flow will start with the system specification and then go successively through several steps, the architectural design, the functional design and logic synthesis, the mapping onto actual circuits, and then the physical design, which is a crucial step that will translate what is actually described as a graph into something that's geometric, that's described with coordinates in a 2D space. And then there will be the verification steps to make sure that this physical design that we came up with is going to satisfy the system specification, is going to be compliant with the design intent. And once we verify that, we go through this important step, which is the tape out. What we call the tape out is sending that design, that geometric description of the chip, to fabrication, and then after it comes from fabrication, it goes through packaging, testing, and out of all these steps come the chip. Now we, in this slide, we actually focus on the physical design because it itself is made of several steps. They go from chip partitioning into major components to chip planning, where these components have to go in the floor plan, to the placements of the subcomponents according to their location in the floor plan, and then other physical design steps that would be, for example, related to routing the clock tree through the chip, routing the power grid through the chip. And then last but not least is to do the signal routing and the verification that all these components all the wires that connected these components are going to satisfy the timing constraints. What we mean by that is, is the chip with all these physical synthesis steps, is the chip going to satisfy the timing constraints? Is it going to run at the clock frequency at which the chip is supposed to run? Now, these steps, of course, they get mapped onto specific design tools that come from CAD vendors. And in this slide, I have given you an academic example in a VLSI course about how they have decided to put up a flow for doing, in-class design of VLSI chip so as to train the students. And in this flow, they have selected various components from tools that are coming from Synopsys and Cadence. The next slide is actually a more specific design flow that's actually more related to the physical design step, where for every step in that physical design flow, options were given. One is actually like a Synopsys option, and the other one is a Cadence option, just to show you that in terms of, let's say, project management in a large project, project managers have options on what to choose for what step, and these options are going to be selected based on various considerations that require a fair amount of expertise. And I will come back to this point because it's really one of the motivation points for using machine learning in VLSI CAD. So what's the bottom line of all this? The bottom line is that for this design flow is that we are going to start with some netlist description that's typically given by a hardware description language. And at the very bottom, we are going to come up with this geometric description of the layout of the chip, okay? And you can imagine that every one of these steps is nothing but a transformation, a mapping, a mapping from a graph to another graph, or a mapping from a graph to a geometry, and then maybe even the geometric transformations will have their own specific steps in terms of placement, in terms of routing, in terms of clock tree, in terms of power grid, and so on and so forth. So now, if you look at every one of these steps, you'll see that you can actually box it in this description. There is a mapping, as I said, a transformation that's going to take inputs, that's going to use some predefined libraries, and out come from this mapping the outputs. So for example, in this physical design step, the input is the netlist, the output is the layout. And with these outputs, we have a bunch of very detailed reports that are related to the quality of the results that have resulted or that have come up from this transformation. Now, to run every one of these steps, we have to use run options, right? These are software programs that implement very complex algorithms. These complex algorithms, they have their parameters, and these parameters have to be set up for any design project. And typically, it's being these design options will get decided by the CAD enablement lead, for the design project. Now, of course, large designs, high-end microprocessors, complex SoCs, they run into IC design cost. And this slide is actually from DARPA. It's showing the almost exponential increase in design cost as we go through our technology nodes up until the 14 nanometer. And DARPA 2 years ago launched this program whose goal is to reduce design costs by improving the automation of the chip design process. Okay, and the name of the program is IDEA, and it stood for Intelligent Design of Electronic Assets. Now, related to this DARPA plot, I have from my old IBM days this other plot that's related to what we call the productivity gap, which is the fact that, although transistors are increasing exponentially, in the chip because of the scaling, because of the additional complexity, because of the additional functional integration, but the number of designers is not increasing exponentially, right? This is a pretty odd plot, but it's still reflective of what's happening nowadays. There is the exponential or the logarithmic scale on the right. That's actually the number of transistors. And then there is the linear scale on the left. That's the number of head count, the designer head count on a given project. And while one is actually increasing very slowly, the other is increasing exponentially. So there is a gap, and this gap is still present. And the goal now of this DARPA IDEA program is to see if, it's an ambitious goal, if we can have a 24-hour turnaround where we would actually generate a layout, okay, for a system on chip or system in package or printed circuit board with no human in the loop. Okay, so 24-hour turnaround time for any of these electronic systems that you see at the bottom, whether it's a processor like the Intel i7 or it's some type of a system in a package. I think this is an RF package. And then there is this PCB instrumentation board from Keysight. So a printed circuit board, a package, and a processor all will have to get layouts in 24 hours with no human in the loop. And the vision the recommendation to implement that vision is to actually see if we can develop models, okay, of these transformations that will allow us to go, let's say, from a netlist description to a layout description in 24 hours. So that's 100% automation, 24-hour turnaround time with no human in the loop, okay? This is to be contrasted with what's happening today, that, if you take the chip on its own, then you have about maybe 9 months. If you take the package on its own, you have 3 months. You take the board on its own, you have 3 months. You add them all up sequentially, for getting a product out. There is about, 1.5 years to 2 years, to reduce that to 24 hours for every one of these steps in the sequence, chip, package, and board. Extremely ambitious, but the solution is indicated as being developing models and training these models. So it has the flavor of a machine learning solution. Now you'd ask, CAD has been in existence for 40 years, 50 years, the age of the Design Automation Conference, the ICCAD, so on and so forth. Aren't we at the point where things are push button, ASIC, isn't it push button? Application-specific integrated circuits using these ASIC flows, or first-time right flows, they are push buttons. The answer is yes and no. I mean, they are push button under the assumption that you have already taken all your steps and you have selected their hyperparameters, meaning their run options. And to be there, you really have to use human expertise. Okay, you have to use experience in chip design. You have to build on your past projects to be able to find out where exactly in the design space or in the tool space you have to choose these parameters. So tools need configurations and selection of the default options so that the entire design project is on the same page in terms of design tool options. There are other things that are actually preventing, CAD from being purely push button, especially, for high-end design, where the verification step actually takes sometimes too long because of the large data sizes. Okay, we have macros for millions of cells. We have, of course, chips with billions of transistors now. The complex algorithms that are running under the cover on all these tools, extremely complex, and they have multiple layers of development. And they would require typically, many iterations to get to a given solution. And if you are doing a high-end product, then you have a large design team that could be actually geographically distributed, and you really have to coordinate, between all these members of the design team, and that will add overhead to your design. And so doing 24 hours, with the context like this one is actually extremely challenging. Now, the other thing is that we have the reports. Now, don't end this. Usually, in academia, we ignore them, right? If you are doing a course, you almost never look at the report. You just want to, show the design and the layout and make a nice presentation. But the output reports are extremely important because they have indicators, or they have the quality of result metrics. And if you want to improve your design, you have to scan these reports and try and find out where exactly you can have promising engineering changes in terms of improving, the design performance, the power, the area, the all the other metrics that you care about in chip design. So, so because of all this, you would ask yourself the question now, these complex transformation steps that are embedded in every single step of the VLSI design flow, can we replace them with inference model? Okay, so this is the translation now from doing something that's algorithmically, let's say, faithful, to the design step, to something that's actually more of a modeling and training flavor, like we see in machine learning. So is there an inference model where, the hyperparameters now are really no longer the hyperparameters of the run options of the design tools, but they are the hyperparameters of the training that we need to use to develop this inference model? Can we do this translation from the CAD space with these boxes of complex algorithms to the machine learning space with these boxes of inference models? And what I'm going to show you in this presentation is that, yes, it's actually possible. And there are many instances of CAD work where such a transition has been accomplished. Let me now make a comment about the deep learning revolution, right? The reason we are talking about machine learning now is because of what happened in 2011 with the work on ImageNet by Geoffrey Hinton and his students on getting incredible image recognition performance from using a deep neural network in which the activation functions were the ReLU functions. Now, and Terry Sinowski also, a couple of years ago, wrote a book. He's also one of the major contributors, not just to machine learning, but also to learning in biological systems. He wrote this book about the deep learning revolution. And also 2 years ago, I attended a tutorial by Helen Lee at CASS, and she gave actually a very nice why are we why deep learning is so hot now. And the reason is because, you know, three forces have joined. The first one, or maybe three currents, three trends have joined together to make deep learning so hot. The first one is the availability of big data. The second one is availability of algorithms, like, for example, backpropagation with the training and supervised learning, and the acceleration of that backpropagation using GPUs. And then the fact that, of course, we have GPUs to help us with this acceleration. Now, the reason I'm mentioning that is because, you know, if you look at CAD and you look at VLSI design, it has actually the three trends have always existed in VLSI CAD. The first one is that VLSI and CAD, they've been really huge sources of big data. Okay, so big data is available to us not just because of the complexity of what's being designed, but also because of all the CAD action that happens around that design. You know, the simulations that we run, the timing analysis that we do, the verification, the layout verification that we do. Every single step is actually a producer of big data. Okay, and so there is so much information there that we can actually extract to learn from our design experience. It's available to us in our input-output, input netlists, output layouts, in our tool configurations, and in our, you know, tool reports. Okay. The other thing is that in terms of algorithmic algorithms, you know, VLSI CAD has always been one of the most advanced fields of practical computer science. Okay, practical computer science, with all the algorithms that we have used, from graph algorithms to logic synthesis algorithms to simulation, circuit simulation algorithms, and so on and so forth. You know, very, very interesting field where the most advanced algorithms in computer science and in numerical simulation have joined together to develop these rigorous design flows. And now, in terms of the use of hardware, it goes without saying. I mean, look at high-end design projects. Their use of existing hardware in terms of the running the design flows is just massive. Just massive in terms of the compute power that we need to run our CAD flows. Okay, so you see, then, you know, deep learning and why it was so hot, and CAD, it's been always very hot because of exactly the same reasons. You know, big data algorithms and the hardware that you use. So we use hardware to build more performing hardware, and that cycle is the I always call it, you know, the invisible hand of the Moore's law. Okay. So now, what I'm going to do, I'm going to share with you a few examples to show you, you know, the fact that in CAD, machine learning wasn't a solution looking for a problem. Okay, it wasn't actually being used as a black box. It was used with actually deep expertise, deep understanding of the CAD problem, the CAD model that we need to use, you know, to solve that problem, and then the ML model that's actually adapted to that CAD problem. Okay, so the in that sense, you know, CAD was actually quite in line with its role of actually doing things in a rigorous manner, because chips, or the success of chip design, would really depend on the rigor we are using to develop these solutions. So I picked up these problems, or these CAD problems, because they will allow me to show you this correspondence between the model that was developed on the CAD side and then the machine learning model that was developed on the machine learning side. It will also allow me to show you the variety of algorithms, of machine learning algorithms that were used to solve these CAD problems. So Let's actually look at the very first problem, which is mass synthesis. It's after you do the physical design, after you generate the layout, you send the chip to fabrication. And when you send the chip to fabrication, you have to go through various steps. And one of the major steps is, of course, the lithography. The lithography step, and that will require that you would take this geometric description of your chip and translate it into a printout, right, on the silicon printout. Basically, you are going to print your geometric description on the silicon wafer through optical means, okay, mainly through optical means and other, semiconductor process means. But here we are going to focus on the optical means because what we are going to do is to show you the transformations that we have to do on the pattern through which we are going to shine the light to print that geometric description on the wafer. So here is an example of that process, the lithographic process. Here is the pattern that you have to make. We call that the mask. It's based on the geometry that you want to print out. And you are going to shine light, and then there will be some interaction between the silicon. And I'm going to skip a few steps here in the interest of time, and also to make things, as approachable as possible. And the issue here is that this lithographic process is actually very far from ideal. Okay, very far from ideal. It's actually you can think of it as a communication channel. And as a communication channel, it has a number of non-idealities. What's being communicated is the layout you want to print, and what's going to be at the output of the communication channel is the printout. And because of the non-idealities, what's going to result is actually very different from your original intent because of the non-idealities. So the problem of mass synthesis is the following. How do I pre-distort, this layout through which I'm going to shine the light, so that after I shine a light, these non-idealities will compensate for these distortions, and out comes a chip that's going to be identical to the design intent. So this idea, this transformation of the layout from something that was clean to something that's distorted to compensate for the non-idealities of the lithographic process called mass synthesis. And to do mass synthesis, the classical way is really to go through technology CAD tools, which are very complex tools that simulate the lithographic process, and also some of the other semiconductor processes like, the resist process, the etching process, the polishing process. All these steps, they can be simulated with very physics-based, very accurate tools. But the simulation is extremely time-consuming. Okay, so here is a location, or here is a step that's a very nice candidate for doing machine learning. Now, also, things actually will get worse as you move from one technology node to another. The pre-correction that you do on the mask to compensate for the non-idealities will become even, more expensive. For example, here is an example from Samsung. Optical pre-correction on 20 nanometer design node is 80x longer than the 40 nanometer optical pre-correction on the optical pre-correction in the 40 nanometer design. Okay, and so 24-hour target actually will become harder and harder to achieve, the deeper we go into our scaling. Okay, so which actually again argue for which again will argue for the use of machine learning steps. So here is what we do. To move from this clean layout to this pre-distorted layout, we have to attach what we call a bias, a change, a small change in the edge. Okay, Now, this bias is going to, of course, depend on the layout and depend on the optics and a lot of other things. And so if I know what bias I need to have, then I can actually form together a learning. I can use a learning paradigm to teach the model how to actually introduce the bias without having to do very accurate, very complex technology CAD simulation. Okay. So the process then would be actually to take the layout and then to come up with a model. That model will be parameterized with some parameters. Okay, and these parameters will have to be identified based on known biases that we derived from previous experience. Okay, so this step of teaching the model how to assign the bias is actually a learning step. And this transformation that we are going to do from the layout to a bias layout or to an optically pre-corrected layout is the inference that's going to happen based on this machine learning model. Now, the CAD expertise, where is it going to show up? It's going to show up in the choice of these parameters. Okay, they are not going to be anything, right? You know, this is the input that's going to go into your model, and that's not going to be just the layout. It's going to be some intelligent input where CAD expertise is going to be really crucial. And there are so many ways we can actually pick up these parameters. But given the optical nature of the step, right, the lithographic step, the most appropriate parameters are based on what we call PFTs, of polar Fourier transform basis functions. And you can imagine that the intensity of the light that you want to shine or use to print the pattern will be related to these polar Fourier transforms through a linear formula that's similar to what I'm pointing to here. I'm not going to go through the details, but this is really just meant to illustrate the fact that my input is not just the layout, it's not the geometric description, but something that will take into account the nature of the process that I want to model, the nature of the step that I really want to. So once I select these parameters, and in this case, they are the CK parameters, I take these CK parameters and put them through in this case, you know, a machine learning or a neural network. We call that a neural network. It's made of layers, and the layers are connected through links, and every one of these links has a weight, and there is a training process that would allow us to compute these weights based on the input signals and then the labeled output signals. So with this model, we can develop now a process, an inference process, where you give me the layout, okay? And then from that layout, you have to go through the parameterization step. You take these parameters, you put them through the model, okay? And then out comes the bias that I need to attach to the edge, okay? And you see that there is a huge gain by choosing these PFT. If you choose another set of patterns, then the number of parameters is going to increase. If you increase the number of parameters, then the size of the network is going to increase. If the size of the network has increased, then the training of the network will become more complex. Okay, and so this is, again, to show you that domain expertise is really essential in the success of these machine learning models, especially in this CAD context. Now, once you have a model like this, you can actually move in really interesting directions. For example, in this simulation or in this implementation, they have come up with a hybrid model where some of the steps or maybe some knowledge is acquired through the physics-based simulation, or we call that the MB, the model-based simulation, and some others are actually coming through the machine learning model. And you can actually combine these two sources of input and come up with a process, or with an inference, or with a bias computation process that's actually much better than the model-based approach. Okay, much better in two ways. The first is in terms of reducing the number of iterations that you need to get the biases, and the second in terms of the quality of the result. Okay, and the quality of the result here is expressed by what we call the error edge placement error, the EPE. Okay, so you see for a given number of iteration, the hybrid OPC has resulted in a much smaller number of EPEs. Here's the second example now. So yes, we go through some pain to do the optical pre-correction, but still at the end we will still get some problems in the layout. Okay, and that will result in what we call hotspots. Okay, so what are hotspots? The lithographic hotspots are special layout patterns that will tend to fail to print. Okay, that will even if we use these optical resolution enhancement technique. Okay, the RETs. And so an important aspect then, of CAD to ensure the success of the design is to detect these hotspots. So detection of hotspot is really a pattern classification problem. Okay, meaning, is this pattern going to result in a failure of printing or not? So either yes or no. And again, there is a feeling that, yeah, this could actually be done in two ways. Either you do the super accurate simulation using technology CAD tools, or if you can recognize the pattern, and then based on pattern recognition, you can decide whether it's yes or no. Is it a hotspot or not a hotspot? And for you to be able to recognize the pattern, you have to extract the features of the pattern. And so there are several ways of extracting pattern features. There are, for example, the fragment signature way that you see here. There is also what we call the concentric circle area sampling, where you put concentric circle in a given pattern and you sample. And at every sample, you say, is there a part of the layout or not? So it's going to be like a 1 or 0 type of a pattern. At this location, is there, let's say you are doing metal M1, is there metal M1 or not? So if there is, then it's 1. If there is not, then there is, then it's 0. So that's the way you can design these features. There are other more sophisticated ways of developing features for hotspot detection. One of them is shown here from a very recent paper, 2019, where we would take the layout and then segment it into a grid. And then in every cell of the grid, we do a transformation, okay? Similar to the Fourier transformation, we call that discrete cosine transformation. Why it's natural to think about these transformations for these layouts? Because layouts, they are really like images, like 2D images. So, and you saw that in the mask synthesis case, they thought about the polar Fourier transform. In this context, for hotspot detection, they are using the discrete cosine transform. Discrete cosine transform is actually used for image compression, okay? And so here it's actually used for detecting or finding features in every cell. And as these features will get assembled, so what are these features? They are the coefficients of the discrete cosine transform. Every grid will have its own features, its own discrete cosine transform, and then they get concatenated in the DCT, a tensor, right? Because it's a grid, it's a matrix, and then every matrix has its own discrete cosine transform. So it's a 3-dimensional array. We call it a tensor. In this work, it was the tensor that was actually used as a feature that would go into a machine learning model. Another possibility is actually to look at the design itself, and then look at the 1-0 type of pattern. Is there a metal, if you are doing, let's say, metal 1, or there is not a metal, and so 1 will be metal, 0 will not be metal, and then to pass this pattern through a deep neural network of the type that I'm going to show you. So here is the DCT tensor going through several layers of machine learning network, where the patterns will be processed with filters, 2D filters, and now it's known under convolutional neural network. The gain that we have achieved by using convolutional neural network is that instead of having the weights on the links arbitrary, like in a generic neural network, now the links are really not arbitrary. There is some weight sharing. Okay, all the filters of the convolutional neural network, they have the same weights as they scan through the image, and so this is a great economy that we have achieved in terms of training these neural networks. And so what's going to be the net result is that, is there a hotspot or there's no hotspot? Okay. The other algorithm also went through, or the other feature set went also through a similar network, convolutional layer, and then some nonlinear processing layer. We call that the max pooling layer. And at the end, we have a classification of hotspot versus not hotspot. Now, of course, training of these neural networks is very important, and there are so many algorithms. The best known algorithm is backpropagation, in which we do a gradient descent, and the name of the gradient descent algorithm we use is called stochastic gradient descent. In this particular piece of work, they used a mini batch gradient descent, and you see the impact of this mini batch on the quality of the learning here. And you see that the mini batch allowed you to reduce the loss function very quickly and to stay stable, through the iterations of the gradient descent algorithm. That's the red, the mini batch, while the stochastic, the traditional gradient descent, was actually a little bit, random in terms of converging to a solution. It has taken many more steps than the mini batch gradient descent. And in this table, it's actually a nice table, because David Pan and his student actually looked also at the work, at the earlier work using the tensor DCT, and did this comparison in terms of accuracy, the number of false alarm, and for a variety of circuits. Some of them are academic, and some of them are industrial. So the point that I would like to make here is the following. Whenever you have a classification problem like this one, hotspot versus not hotspot, one of the major issues is that the data is not balanced, in the sense that, yes, we have a fair amount of data. It is a big data problem, but the classes are not balanced. There is a minority class and there's a majority class. The majority class, of course, is that, most of the patterns, the absolute majority of the patterns, they are not hotspots. Okay, they are going to be printable. And it's only a small minority of the patterns, is going to develop a hotspot, and they are not going to be easily printable. And so there is an imbalance in the terms of the size of the classes. And whenever you have imbalance, just looking at the accuracy of the inference is really not sufficient. What you really have to look at is something that's beyond accuracy. And here I'm alluding to what you have to look at. You have to look at of course, the false positive rate or the false alarm. But there is another thing that you have to look at. Rather than accuracy, you have to look at the true positives. And the next example will allow me to illustrate this issue with any classification problem we might run into, is the fact, how do we fix this class imbalance? that we have a minority class versus a majority class. So here is another instance where such an imbalance might show up, is when you are actually doing yield analysis, and you want to have packages that are let's say high end, in the sense that they really don't have any failed chips inside. So it is, the example here is coming from stacking memory chips in a package, like the 3-dimensional memory chips that are now very, very common in all kinds of products. Now we take the memory dies, right? And some of these dies are good, some of them are bad. The majority, of course, are good. But what we are going to do is that we are going to take these good and bad memory chips and stack them in a package. And then we are going to test the package, right? And then some of the packages will have all good chips, they are the high-end products. And some of the other packages, they are going to have a chip that's actually bad. And so it's going to be basically a 3D memory, but the size of the memory is less than the high-end product, okay? Because we have a failed chip inside. And you can actually compute the probability of having a package fail after you stack all these chips. And it's going to be actually proportional to the probability of having a die fail. And the proportionality factor is basically the number of chips that we have to stack to form the package. Okay. Now the question arises, is there something I can do to increase the probability of having a good package after I stack all these chips? And the way to do it is, yes, if you can actually, instead of taking these dies randomly out of the wafer and packaging them, randomly without any insight, is if I can develop a classifier, something that will actually look at the chip one by one and will help me say, yeah, this is in the good lot, this is in the bad lot. Of course, the classifier is not going to be perfect. It's going to make errors. But the errors that we will be making in the classifier will be much less than doing things at random, okay? Now, the issue of class size, of course, will show up here. Why? Because if everything is working correctly in my production line, I'll have less bad chips, much less bad chips than good chips. And the classifier will help me increase the probability of having good chips in the package. And here is an example. If I take my dies, the chips, through the classifier, I predict them as good, okay, based on my classifier, then these are going to be packaged. I'll have a higher probability of packaging good chips, with the net result being that instead of having just one high-end product out of 4, now I have 2 out of 4, and then the other 2 will be low-end product. So I have basically increased the number, I have enhanced my yield at the package level by a factor of 2, just because of this classifier. So here is the message that I want to share with you for why it's so important now to look at classification, not from the viewpoint of accuracy, but from the viewpoint of the false positive rate and the true positive rate. So the true positive are, the declaring a bad chip bad, okay? That's a true positive. And then the false positive is declaring a good chip bad, okay? That's false positive. So if you, let's say, ignore this metric, and let's say you have 2% bad dies, in your lot, you have only 2% of bad dies, and you can develop a trivial classifier that's going to declare all the dies good, okay? What's the error you are going to make? 2%. What's the accuracy? 98%. But this is meaningless for really yield enhancement. What we'd like to make sure of is really the following. We would like to make sure that the true positive is going to be as small as possible, okay? And that also the true positive is going to be as high as possible, meaning I'm going to find the bad chips, right? I'm going to find the bad chips. And also, I'm not going to declare any good chip bad. So I'm going to reduce the false positive, okay, and increase the true positive, which means that I'm going to be, in terms of my classification, somewhere in this top left corner of this plot, which we call the receiver operating curve, or the receiver operating characteristics. It's a plot that actually comes from radar for identifying whether, you know, a flying plane is a friend or a foe. Okay, it's exactly the same problem. You want to declare a foe, and you don't want to declare a friend a foe. Okay, and so you have to push your decision algorithm for in your radar signal processing toward this top left corner, and that's exactly the same problem in this classification. I'm going to skip now these slides because they are actually very technical, and but the idea of how to improve these receiver operating characteristics is actually by doing a sampling process that we call random undersampling, and then use a classifier that's called a boosted classifier. So it's a combination of two operations that we are going to do above and beyond the simple classification that's based on maybe regression analysis. We're going to deal with the rare data problem for the bad chips, and we are going to deal with the accuracy, or sorry, the false alarm and the true positive problem by the rare data is going to be dealt with random undersampling, and then the pushing the operating point to the top left corner will be done through a classifier boosting. And you see here, you know, if you really don't do this algorithm called RUS boost, which combine the data undersampling with boosting, you're going to have this ROC. If you do both, then, you know, your ROC is exactly what I described to you, which is, it's going to be something that's close to the top left corner, where we are going to have very small false alarms and very high true alarms. Okay. So Ricardo, am I doing okay on time, or?
So please go ahead, no problem.
Okay, so let me move to the next problem now. And it is related to the earlier problem in the following sense. This memory that I told you about, this memory packaging, you know, doing 3D memory packaging and doing yield enhancement at the package level. Of course, you need to test these chips, right? And to be able to develop a classifier, you need to train the classifier, and you train the classifier by doing some tests and developing some data, okay? Now, the number of electrical measurements that you have to do per die, okay, for developing the data to be able to do the classifier for this particular memory packaging issue is actually 1,000 electrical parameters per die, okay? So if you have 200 dies per wafer, that's 200,000 electrical parameters. If you multiply that by the number of wafers of lot, you have tons of measurements, okay? Tons and tons of measurements. So is there anything we can do to reduce the number of measurements, okay? To reduce the load, okay, the workload of post-silicon testing. So this is exactly what this problem is about now, is, you know, you are going to see machine learning, you know, showing up in a very interesting way to help you reduce the number of measurements that you are going to do post-silicon, so as to develop, you know, the data that you need to do yield enhancement, and to also, you know, train maybe classifiers for yield enhancement. So the idea here is called the virtual probe. And the idea of the virtual probe is the following, is we need to replace the test structures that we put on the dies inside or in between dies on the wafer, replace them with estimates, okay? How are we going to get the estimates? By developing a model, and we are going to train the model based on the measurements that we have. Okay, so you can think of it as an interpolation problem. What do I mean by interpolation? Where we have a location here on the wafer, okay, and you know the data in the neighborhood of that location, and you want to infer from the neighboring data or the neighboring measurements the measurement that you have where you don't have a test structure. Okay, so this approach is actually a machine learning approach, and that's going to be solvable through a machine learning algorithm. But why is it solvable? Okay, I'll explain to you why is it solvable, why we can get away with a fewer number of measurements, and we are going to achieve, you know, the required accuracy on these measurements, so that we can use the virtual data now in downstream for developing classifiers. Now here is the a wafer example. I showed you, I say 200 chips per wafer. In fact, it could be up to 300. This is 282. And in this wafer map, they have measured leakage currents, you know, across all the dies in the wafer. And you see in this normalized color plot how the leakage current will change, you know, die to die through the wafer. Now, there are many advantages for developing virtual probes. Of course, less area overhead for test structures, right? You know, you are not, the test structure is not going to take silicon area anymore. You can actually devote that silicon area to something more useful than just doing a test. You are going to be able to do faster testing. So instead of going to the taking, you know, physical probes and probing the wafer for getting the measurements, you know, you are going to be able to use software to come up with this data. And then last but not least, you know, whenever you put a probe on a wafer, it's a mechanical operation, and there is some likelihood that you are going to break something. Okay, so there is a reliability aspect that you will be able to improve in terms of wafer measurement by going into the virtual probe approach. Now, why is this solvable? Why can we get away with a fewer number of measurements than a full set of measurements throughout the all the dies in the wafer? It's because of this observation. If you take, let's say, the leakage current map, okay, wafer scale, and you do again our friend the discrete cosine transform. Remember discrete cosine transform that we use in hotspot detection? We applied it on a grid of cells, right, that covered the layout. Here we are applying discrete cosine transform on the whole wafer. And the observation here is that, look at the discrete cosine transform, is extremely sparse. Okay, it has only a few number of non-zero coefficients. And these non-zero coefficients, you know, will get distributed, you know, at low frequencies, high frequencies. What we mean here by frequencies is the jumps, the color jumps that you see in the wafer map. Okay? So the reason this is solvable is because in the discrete cosine transform, we can describe the full map with a small number of discrete cosine transform coefficients. It's exactly the image compression problem that you can convey, you know, the content of the image, the visual image, by doing an inverse discrete cosine transform on the sparse coefficients that you come up with. And that's the very reason why the virtual probe is doable. And here I have shown from this paper by Tao and collaborators. Here is the measured leakage current, and here is the estimated current based on few measurements and the virtual probe. And you see visually that they are actually very close to each other. So this is leakage current measurements. There's also flush delay, we call flush delay measurements. These are delays that go through scan chains, also distributed throughout the wafer. And again, you see that, you know, this is the full measured wafer. And here you have the few measurements plus the virtual probes. And the other comparison is really comparing what's happening in the discrete cosine transform for the measurements versus the discrete cosine transform for what got estimated. And you see that they are actually also very close to each other. Okay. Okay. So now here is a twist on discrete cosine transform and the virtual probe and all that. Okay. As I told you, what we are doing basically is an interpolation, right? We are taking these few measurements and interpolating for the value of the measurement in between, for the locations where we don't have measurement, we estimate. Okay. And so you can think about it as this interpolation function f taking a location and then estimating the value of the probe. Okay, estimating the value of the probe where we don't have a measurement. Now, the question is, what if we have data discontinuities, like you see in this wafer map? Okay, you have a huge jump between, red and blue. Red is at the top, blue at the bottom. Discontinuity. Okay. The other thing is that, what about measurement uncertainties? I didn't talk about them for the virtual probe. Every probing, every measurement has uncertainties. How do we account for the uncertainties in the probe? Okay, and the virtual probe. And then the last but not least, I told you about the measurements as if they were totally separate, totally uncorrelated, independent of each other. What if I have some coherence in the measurements, meaning neighboring dies, will have similar measurements. So there is some correlation. Okay, so these will require that we develop more sophisticated, models, also using machine learning to account for discontinuities and to account for correlation between neighboring measurements. So here, this is a 3D map where that will show you something that's smooth, in which the virtual probe will work fine, okay, and something that's really not smooth at all, where there is a discontinuity, where the virtual probe will have some difficulties. So let's look at now this idea of taking into account, discontinuities and how we are going to process them. And for this, I'm going to take an interlude, or take a break, and show you now in this CAD context, the difference between supervised and unsupervised. In all the previous examples, up until, from the mass synthesis to the virtual probe, we actually looked at learning models where we have labeled output information. So the labeled output informations could be measurements, could be detailed simulation runs, but we always had, labeled output. The mass synthesis was the bias. From previous experience, we had the edge bias available to us. Okay. In the virtual probe, it was a measurement that was already available to us. Okay. In the hotspot, it was the fact that we knew for the certain pattern that there was a hotspot, and therefore we can train the classifier to recognize the hotspot. Okay. So all these examples are instances of what we call supervised learning. Now, when we come to the discontinuity in the data, the measurements are presented to us, wafer scale measurements, and we are not going to eyeball them, right? Somehow we have to find structure in this data. Somehow we have to determine where the discontinuities are. So presenting the data with us without the measurements being labeled, or without the edges being labeled as edges of discontinuity versus, non-discontinuity, that's not going to be available to us. We have to find it ourselves. We have to find the structure in the data ourselves, and finding structure in the data is what unsupervised learning is about. Okay. So let me share with you this example, therefore, and one of the most important algorithms for unsupervised learning is called the k-means clustering algorithm, and it can apply directly to this discontinuity problem in the wafer measurements. So red versus green in this example, okay, and the idea here is really to look at these measurements and cluster them together so as to distinguish, the green from the red. Okay, And that's going to be done automatically without having any labels on the data, except what's being made available to us through measurements. So the mean clustering algorithm would take the number of clusters, okay? That's a hyperparameter of the algorithm. And then it will start with some estimates of the mean location of every cluster. So here we have 2 clusters. So the mean location is the coordinates. That's going to be the center of mass of all the members of that cluster. Okay, so first we estimate that center of mass, and then we iterate. Okay, we iterate on that estimate until we converge, until the center of mass of these clusters will stop changing. Okay, at which time we have a distinguished, or we have segmented our data into clusters. Now, the most important hyperparameter is K. K has to be known ahead of time for us to be running the algorithm. But what if you don't have K? Well, you know, they have developed algorithms for coming up with K. One of them is called the, you see, it's a Kalinski-Harabas index, something that you don't learn when you take your basic, you know, machine learning course, but it's something that's really available, and you can actually use to get the best number of clusters before you run the k-means clustering algorithms. And here is the net result. The net result, I showed you this measurement map for the wafer. Okay, if you run virtual probe without you being aware of the existence of these discontinuities, you know, you are going to get, you know, this wafer map. Okay, these estimates really bad. Okay. Now, if you develop a more sophisticated algorithm, so you call it the Gaussian process, where you have, you know, the correlation captured, and you also have the discontinuity structured captured, then you get this estimate of the data, okay, based on the model and based on the clustering. And you see that they are actually very, very close to each other. Okay. Now, the bottom one, the bottom left result is actually when you have a Gaussian process where correlation is being accounted for, but the discontinuity in the data is not accounted for. Okay, at which time you're going to get also this bad result in terms of matching the actual measurements. You see, in this machine learning example, what we have a combination of 2 things. You know, a combination of doing unsupervised learning for getting the clusters, and for doing supervised learning for coming up with a correlation model of our data. And if you combine the 2, then you will have this faithful reproduction of the original measurements. Now, in the remaining slides, we talk about the importance of developing this correlation model. These set of methods are called, you know, kernel methods or kernel estimation methods. But what I would like to share with you here is the fact that developing these correlation models implicitly assumes, of course, that we have a probabilistic framework, right, for developing processes or 2D processes where correlation is being accounted for. And so the learning is going to be of a probabilistic nature, where the cost functions are going to be formulated in terms of probabilities, okay? And so you are going to take your data, you are going to sample your data, and then you are going to develop a cost function that's going to be based on the probability of the model that you have given the data that you have been given. Okay, so here the probability that you want, or the model that you want, is the correlation, right? You know how 2 neighboring points are going to be correlated. And you have many candidates for computing that correlation. Okay. These candidates, everyone will have some likelihood based on the data that you have been given. And what you are going to be doing, you are going to maximize the likelihood of coming up with a given kernel given the data that you were given. So this optimization problem based on the maximization of the probability is sometimes called maximum a posteriori estimation. Why? Because we are estimating the a posteriori probability of the model given the data that we were given, the coordinates and the measurements. In this case, the coordinates of the measurement point and then the value of the measurement. Okay, and then we pick up, as I said, the model, the correlation model that would correspond to the highest probability. Now, the correlation model has its own parameters. Okay, for example, a correlation distance. Like how far do they have to be for them to feel correlation? That correlation distance is a parameter of the model that will also have to be estimated based on the data and the kernel. Okay. So this is the let's call it the influence distance of the kernel. And so these approaches now for doing machine learning, they are called Bayesian learning approach learning, and they are based on, as I said, probabilistic models. For example, the development of the a posteriori kernel probabilities, is based on using the Bayes rule. And again, I'm not going to get into the details, but I'm going to show you the result of using these correlation models in terms of reproducing the actual measurement. We went through a series of models here. First, the Gaussian process, the Gaussian process with progressive sampling, the Gaussian process with spatial-temporal effects taken into account. So if you do progressive sampling, spatial-temporal effects, and the Gaussian process all together, you compare the bottom one with the top one here, okay, the measured with these, you see that we have been able to reproduce the result quite faithfully, okay? Now I'm come to my second interlude, which is these probabilistic learning models. They get actually classified in two major categories. The first one is called the discriminative category or model, and the second one is generative category. For example, if you have a classification problem and you want to know, is it in class A or class B? And all you want is really the boundary between the two classes. That's typically a discriminative model, okay? For which you need to only know the conditional probability of the output given the input. Okay, that's all you need to know for developing these discriminative models. On the other hand, if you really want to know not just the boundary between the two classes, but also within every class, what's the distribution of elements in the class, then you are dealing with a generative model. Okay, and for the generative model, you need actually the joint probability distribution of the input and the output. And if you have that joint probability distribution of input and output, you can generate, of course, the conditional, you can generate the marginal. You have actually full access to the probabilistic model and how input and output, correlate with each other. And this is actually the most I would say sophisticated model you can develop. It allows you to do all kinds of computations. In particular, it allows you to generate synthetic data, because once you have the probability distribution of the elements within every class, if your class is a minority class, but your probability distribution of your minority elements, then you can sample that probability distribution to generate more points. Okay, and therefore reduce the imbalance between the two classes. That will connect me now to what we call the imbalance issue, for which we had to develop, random undersampling. We had to develop some boosting classifiers and so on and so forth. With a generative model, you can actually proceed in a more direct way and do generative sampling, generate synthetic data to deal with imbalance in your data. Of course, it allows other kinds of learning, like Bayesian learning. Examples, for example, the virtual probe and the wafer scale correlation examples are actually based on generative models. On the other hand, the hotspot detection and the yield improvement were discriminative models. So I'm going to skip this example. It's a very interesting example, but in the interest of time, I have already taken 15, maybe possibly 20 minutes more than my allotted time, and I'm going to skip the circuit aging example. But the point I would like to make is that for all these CAD examples where we tied up the CAD model to the machine learning model, having domain expertise was very crucial, right? You can't really treat things as a black box. You cannot just take like the wafer map and treat it as if it were any image and say, let's do deep learning on it, the same way you do it in image recognition. You really had to look more carefully and develop the features that you want to pass through your machine learning algorithm. Now, of course, I have shared with you just maybe 6 examples with the example that I skipped, but there are many, many other examples that illustrate the widespread use of machine learning in VLSI computer-aided design. And you can see some of these examples in this 2019 edited book of ours. For example, interesting examples is that will even illustrate even further machine learning is how we deal with the failure events for failure analysis. Again, it has the flavor of a data imbalance, because failure by definition is really not common, it's rare. And so you have to develop algorithms where the number of data point is actually small. A machine learning for analog design and circuit simulation, machine learning for performance analysis. Interesting directions that I don't have the time to share with you is machine learning for logic synthesis, especially in terms of using recommender systems for recommending specific logic synthesis flows. Parasitic extraction using random forest machine learning. Okay, in DAC of last year, there was a really interesting paper from Intel about using random forests as a model for accelerating parasitic extraction. Machine learning frameworks and physical design acceleration. In this very seminar series, Professor David Pan, a few months back, actually gave us a very nice example about how to use the framework, meaning all the parallel processing that we have developed, all the Python code that we have developed, all the TensorFlow that we have developed in the machine learning context, and bring it to bear on a physical design problem like the placement problem. And by building some analogies between the two, one could use the machine learning computational framework now to accelerate the physical design step. And in this case, it was the placement step. Okay. Also, very recently, analog layout synthesis combined with Bayesian learning has been proposed, and very recently in some of the CAD conferences. Also, while preparing for this presentation, I came across a paper that was actually published this month in the ACM Transactions in Design Automation of Electronic Systems. And it's actually machine learning for electronic design automation, a survey. It has a very nice intersection with my presentation. And of course, I would encourage you to go ahead and check this paper. It has nice tables showing also the widespread use of machine learning in VLSI. So I'd like to thank you very, very much for your patience. It took a little bit too long to cover my presentation, and I'll be happy to take any questions you may have. Thank you very much.
So thank you very much, Abe. Very nice talk. We have here some questions. So first one is from by Lou Schaffer. Is 24 hours possible? I think the sum of the runtime of all the programs needed is longer than 24 hours. Often DRC alone takes that long.
Yeah, no, I 100%. So I think the 24 hours was actually for just the layout generation and netlist to, let's say, Verilog netlist to layout generation. So going through just the physical design without any verification. So any post layout verification, parasitic extraction, LVS, design rule checking, all this, I don't think it was really included in that 24-hour target. And so I definitely agree with Lou that, if you want to sum up all the design and verification steps that you have to go through, it's not going to be achievable in 24 hours. It will take longer, and I really don't know other than trying our best to introduce machine learning in every single verification step, how much we can compress, but again, I don't think it's going to be 24 hours for the full design and verification flow. I agree with you.
It also depends on the size of the circuit.
Absolutely. But I come from a microprocessor design, so for me, anything is a very complex microprocessor.
Okay, thank you very much. So now a question by Sai Charan from OmSemi in India. So will customers feel comfortable on the possibility on the probability-based results in designing chips when they use AI-based EDA tools?
I think it's all going to depend on the quality of results. As I told you, even now with the current tools that we have, even without machine learning, we have these reports that are actually extremely detailed and give you a very good idea about the quality of results that any CAD steps achieves. So the way to convince customers is really by comparing the quality of results of the actual CAD step without machine learning with the one that you obtain with machine learning. And if they match, then I don't see a reason for why customers wouldn't feel comfortable. If they don't match, then whoever is proposing machine learning, they should go back and actually work harder. Otherwise, we'll keep using the non-machine learning solution.
Okay, another question by Sai Charan. For a person who is currently working on in the EDA industry, how challenging is to stand strong in using AI-based EDA tools?
So my understanding of this question is, what if I want to reformulate this question? How solid is it now in terms of proposing machine learning solution in CAD? Am I correct? Or in EDA? How solid is it in terms of a track? Am I correct?
Yeah.
Yeah. It's actually solid enough. And if you look, for example, I run actually a workshop, and that's co-located with ICCAD. It's called the ACAD, the Accelerator CAD Workshop. And we have industry presence from Cadence and Synopsys. And both these companies actually have a very solid roadmap in terms of incorporating machine learning inside their tools. In fact, hotspot detection, let me give you one example because I mentioned that in my own presentation. Hotspot detection, machine learning has been used in hotspot detection for quite some time, even in industry. And I know for a fact that, one major foundry was actually using machine learning to detect hotspot in their layouts. and so at a production level. So in terms of how solid, it's actually very solid because it's in industrial use for that particular problem. Now, of course, the idea is really to spread this over. And if you look at this DARPA program about the 24 hours, the idea is, to see if we can move such paradigm to layout generation now for logic design. And so I think there is attached to that program, there is a really nice work that's being done. And in fact, that work is also industry monitored, and some of it actually is even industry driven, because that's really the frame or the framework that DARPA has defined for this IDEA program, is for industry involvement to be upfront rather than after the fact. And so my assessment is that yes, very soon we will be actually seeing many of these algorithms being transferred into industrial use.
So another question by Sai Sharan. Can you please resource for the 29th slide, interesting directions?
Okay.
So maybe you can put the slide again.
Sure. Am I still sharing my screen, Ricardo?
Yes, your screen is being sharing.
Okay. So slide number 59. Okay, let me go there. Wow, that's a huge number of slides there. Okay, here it is. What's the question about this slide?
Can you please resources? So we want you to give some more information about this topic.
Oh, yeah, absolutely. For example, logic synthesis and recommender systems. In fact, there is the work by IBM on using recommender systems in logic synthesis. In fact, IBM, again, you are asking me about how solid machine learning is in the context of CAD. Over the past 10 years, IBM has been using a SynTune Synth. Okay, it's a machine learning framework for doing logic synthesis that has been used on Z series microprocessors, the microprocessors that go into the IBM mainframe. And in this regard, you can look at the publications of Matt Ziegler and his collaborators. Okay, so that's one pointer I can give you. Parasitic extraction and random forests. This is work by Intel. I had the exact reference that I can actually find for you, if you don't mind. Or I can maybe, in the interest of time, maybe I can get your email from Ricardo, and I can send you the exact reference. So it's a paper that was published by Intel at DAC 2020. A machine learning framework and physical design acceleration. That's work by David Pan and his group. In fact, the journal version, that the original work was in DAC 2019, but the journal version of this work, it was published in April of 2021 in the TCAD. Okay, and the transactions on CAD. And then analog layout and synthesis and Bayesian learning. This is work out of University of Minnesota with Ramesh Hajani and possibly also Professor Sachin working in this area. And then I can give you also a few references on this. Okay.
Okay, thank you. So now another question by Lou Sheffer from USA. So our speaker of next week. So do you find examples where machine learning does not help? We tried this once with placement algorithm, but found the best parameters hard to predict.
So I would then maybe refer Lou to again this work by David Pan and his group on accelerating placement using machine learning frameworks, where actually some of the work went into matching the hyperparameters, right? The hyperparameters of the placement formulation as an optimization problem with the parameters of the cost function of the machine learning problem. And I think there is a lot of work that's happening right now in hyperparameter selection in the machine learning context, and that could be actually brought to bear once we find this analogy, or once we find this correspondence between the machine learning optimization problem and the CAD optimization problem. We should be able to bring this hyperparameter selection work to bear on CAD. And so, Lou, I'm a little bit more optimistic than the work that was maybe done 10 years ago or maybe 15 years ago, in terms of machine learning for some of the CAD problems. Have I answered the question? Hello? Ricardo, do you hear me?
Okay, so we have, well, Lou. Okay. So by Deepa Kota from Texas. Hear me? So Deepa Kota, are you hearing me? Hi. Are you listening to me?
Yes, I can hear you.
So there is a question by
you,
Deepa Kota. Deepa Kota from USA, University of North Texas. Are there any challenges for applying machine learning algorithms on VLSI design flow?
Yeah, many challenges. But I think the most important challenge is really to understand your features and understand the features that you want to present to the machine learning algorithm so that you can get reliable inferences, accurate inferences. I would say that this is the most important challenge. And in fact, that's really the most difficult step. It's the feature engineering of the CAD problem. And once you figure out that step, then it will be possible to apply many of the machine learning techniques. And as I showed you, we've covered a good territory in terms of the various machine learning algorithms. I showed you supervised learning, unsupervised learning, clustering, classification, boosted classification. I didn't talk about, for example, support vector machine, about deep learning. Of course, it has been used. Now, the Bayesian learning, of course, it has been used. But I would say the most important thing is really the CAD model and the feature engineering of the CAD model. If we work out the details of that aspect, then the machine learning will actually be doable, or let's say, we will be able to have, more confidence, let's say, in the machine learning output.
Okay, thank you. Lou answer here in the chat saying, yes, thanks. We tried this about a decade ago, but techniques are better now.
Right.
So
I agree with Lou.
Okay, so I have a final question. Is in my opinion, nowadays we are using much more transistor than is needed to design a chip. So the traditional standard cell methodology, we have a few combination of functions in a cell library, and this provides to use more transistor than is needed. You think that machine learning can also help this on optimizing the number of transistor that we are using, considering that we should also have another tools to do the generation of each needed cell, no, that is the output of the logical step, no?
So I think this question, if I understand it well, is related to logic minimization, right? So you really want to have the most compact representation of your Boolean function. Okay, and logic synthesis tools, that's exactly what they do. And if we want to maybe incorporate machine learning into logic synthesis tools so that they can do this job better, I think this is quite conceivable. Now, going back to one slide I shared with you in my presentation, I shared with you the productivity gap slide, and it's really an IBM slide from way back, from, again, about 10 years ago. Like Lou was saying, we tried these things 10 years ago. Now, there was actually the way IBM approached that gap wasn't actually through machine learning back then. Okay, again, in agreement with a statement that Lou made, but it was by developing a methodology called large block synthesis. Okay, so it was an expansion or maybe a reduction of a custom design, right? Of custom transistor design, and a move toward using logic synthesis throughout the high-end design, throughout the microprocessor. And so it's very conceivable that we can actually go back to large block synthesis and maybe improve its output in terms of minimizing the number of gates that result from such synthesis, and maybe machine learning will be helpful. Maybe this is something that's already being worked on, but something that's already worked on is that after they developed the large block synthesis approach, as I told you, the work by Matt Ziegler and his collaborators was actually to go into this logic synthesis flow and even develop it further by doing what? By actually looking at the hyperparameters of the logic synthesis flow and use machine learning and past design experience to develop procedures or policies for picking up the hyperparameters of the logic design flow. So that's a promising direction. It's and it ties up with what I mentioned about using recommender systems in tool flows and in CAD methodologies. Any other questions?
Okay, thank you very much, Abe.
Thank you, Ricardo.
Just last comment that in your talk you have done a reference to the work of Lee.
Yes, Helen Lee. I had a couple of slides from one slide
has a
from
recorded talk available in our CASS YouTube channel.
Excellent.
It's happening.
I can hear you, Ricardo. Somehow the audio. Your audio is not.
Can you hear me now?
Yeah, absolutely. I can hear you now.
Yeah, well. So I would like to invite all you to return next week to the IEEE CASS Rio Grande do Sul Talks 2021. As you can see, we are going to have a very interesting talk by Dr. Lou Sheffer from Howard Hughes Medical Institute. And the title is The Electrical Design of Biological Systems. What can you learn from the brain of a fly? So Lou Sheffer has a long experience working with Cadence, and since several years, he's with the Howard Hughes Medical Institute. So you are going to have a very exciting talk also next week. I hope to see all you next week in this same hour. And the week after, we are going to have a talk by Dr. Yervan Zoyan from Synopsys, Safety and Reliability Challenge in Today's Autonomous Vehicles. And the week after, July 2nd, Professor Fernando Silveira from Universidad de la República in Uruguay, talking about wearable medical devices, sensing and powering from a distance. So thank you to all you for attending this very nice talk by Professor Ibrahim Elfadel today. And so take care and see you next week. Bye-bye.
Thank you. Bye.